I don't know if there's any official rules regarding a quorum. I can,
50%, but I don't know.
oh, but in terms of considering a class to be a quorum. I don't know. I once taught a class of, I think, 27 people and 2 showed up. That was the Thursday before Thanksgiving. Everyone was either left already or at a conference or something else. And so that's why this year we're not having class the Thursday before Thanksgiving. We're not, because no one's going to be here, and those of us who are here are needing a break in that moment in time. You're doing homework, you're doing other things. So, speaking of homework, let's see, Zoomers, can you hear me and see me okay? I'm getting the screen share going so we can all talk about that. There's some thumbs, thank you very much. Got the chat open as per usual. What did I want? Not this, not this. Almost, here we go. So you have 2 things you can be working on now. You're welcome. I wouldn't want you to go into the weekend at a risk of being bored. I mean, what fun would that be? So we have your next formative assessment due on Monday. That one I meant to be more conceptual. So there's no equations. There's no like notation in it. It's more like, in this situation, what can you do? Kinds of questions, because that's the level of information that I hope you'll retain by the end of the semester is, oh, I need to be in this bucket of strategy. Then you can go back to your notes and look for the finer grain details once you figure out, you know, like where the general place you should be is. So that was the intent of that. We will talk about that on Tuesday as usual. And your next homework is also available as of now. You should be able to log in online and do that. That is not due until the 17th, however. This one, so I have it open, just to talk about it very briefly. As I mentioned last time, this one uses very little additional code. Most of the results that you would enter are going to be directly in the output. It does offer the chance to do a sequential process in terms of we add something, talk about what happened, add something else, talk about what happened, because that's a very common process in publishing this research. And there are a lot of, shall I say, greatest hits questions, like questions you've answered several times and hopefully have right by now. And if you don't have it right by now, here's one more chance. Like, what does the standard error of a slope tell us? Broadly construed. Here's one. Zoomers can play too. What does the standard error of a slope tell us? Let's go find one.
How much noise there is?
Yeah. So for instance, the motivation slope standard error indicated which of those drop-down menu choices indicates some kind of inconsistency? That would be the question. So lots of those again. It's a little on the long side, a little on the tedious side, but hopefully we'll provide a nice review heading into the last unit. And again, that is due on the 17th. As I just mentioned, we have no class the Thursday before Thanksgiving, and then a couple formative assessments and one more homework after that. So the last homework is going to be based on material from Unit 5, which means I will try to put it up well in advance. So if you're one of those folks who likes to get your stuff done and get out, I support that, and I encourage that if you're able to. If not, Wednesday of finals week is when I'm calling everything done. That way I have enough time to turn in grades and deal with everything else. So, all right, any questions on that? Good? All right, that's enough for then. Then we have a little bit more of Lecture 4 to talk about, and Example 4B I had built to serve as kind of a general review of this, where we've come so far this semester. Does that work for folks? Why not? So we've been talking about effect size and how to assess differences in effect size across models a little bit. That's where I wanted to pick up. So slide 30 in particular. So this represents an example sequence in terms of how we might add predictors to a model. So what I wanted to talk about is what is necessary at each step to ascertain how the model improved as a function of what you added. So if we start with an empty model, for instance, it only has a fixed intercept. In that case, what does the fixed intercept tell us? Yeah, the sample mean for the outcome. Because that's, if we don't know anything else about a person, the mean, the expected value, is our best guess for what it should be. So let's say hypothetically that at that stage, the variance in my outcome is 200. I only have an intercept giving everyone the same mean, so I have an R-square of 0. I haven't explained anything yet. This is the baseline. Let's say that I add one slope for predictor A, and that reduces my residual variance down to 180. Yay me. That is a reduction of 10%. So proportion 0.1 for my R-square. Now, I have a second column here for the change in the R-square, going from nothing to something. So in this case, does it look like I would need to do some kind of separate investigation as to whether the change in the R-square between the first and second models is significant? If I go from a model with no predictors to a model with one predictor, do I need to do anything different or special to ascertain if that predictor's effect is significant? That's what the test of the model is going to tell me. It's comparing nothing for the R-square to whatever it is currently. And if I have one slope in the model, my test of whether the model is significant is the same information as whether my test for that slope is significant, because the model is the slope. So it's 1-to-1. Now let's go one model down. If I add a slope for predictor B, let's say that my residual variance is now down to 140, bringing my R-square up to 30%. So in this case, I have a change in R-square relative to the previous model with only A of 0.2. So these would be considered nested models because model 2 is a subset of model 3. In this case, after adding one thing, my R-square increased from 0.1 to 0.2. Do I need to do anything here that's extra to assess the change in the R-square? What do we think? Multiple choice question, 50-50. Yes for thumbs up, no for thumbs down. That way the Zoomers can vote too. I got a couple votes. We said one for yes, we got one for no. You were shaking your head, is that a no? She's like, oh no, I don't want to vote anymore. We're done. You want some more candy? Zoomers, you want to vote? Do I need to do anything special, different, extra, to test whether this R-square change of 0.1 to 0.2 is significant? What would I have to do? Let me change the question around. Let's say hypothetically I know, I'm not going to say how I know, but I know that this increase of an R-square of 0.1 to 0.2 is significant. Do I know what caused it? B did, right? That's the only thing that's different. So if I add one new slope to the model, and that one new slope is significant, I know that the R-square addition it created is significant. It's a 1-to-1 correspondence. It's the same concept as going from 1 to 2 by adding one predictor as going from 2 to 3 of adding one predictor. So in each of these cases, the model results tell you everything that you need to know. The model F for the R-square tells you if the variance explained currently is better than nothing. And that's a joint contribution of whatever's in the model. Like at this stage, it's A and B. The change in R-square, the only way this change could have happened is the contribution of this one new slope. Then whether that slope is significant is the test of whether the change is significant in the R-square. Same deal. Now where it gets tricky is going from 3 to 4. Now I have two new slopes, and they did a great job. They brought my residual variance down to 80. My R-square jumped from 0.3 up to 0.6. That is an increase of 0.3 in total. So what does the F from the model tell me in this instance about model 4 here? What would the F test of the model tell me? Maybe I should start throwing the candy. Would that help? I think we discussed this option last time. I'm afraid it might hurt somebody or break a laptop. What does the model F-test tell me at this stage? The model as a whole. Yes, and this is exactly the point I'm trying to drive home here. Like, you will get an F-test for your model as to whether this R square, for instance, of 0.6, is greater than 0 based on the contribution of these four things. But that's answering a different question than did C and D help? So if I want to test whether the change in the R square that C and D together created is significant, that's extra. I got to do something else. Because I want to be able to say, is it C? Is it D? Is it both of them? Now you might say to yourself, well, why would you do C and D at the same time then? Right? Wouldn't it make more sense just to go one by one so that it's clear what helped? Can you think of a case in which I need C and D at the same time? Like in any of the examples that we've done so far? Do all predictors only need one slope, or sometimes do they need more than one? Yeah, that's where I'm going with this. Like if this was one dummy code for a group difference and this was the other one that you needed for 3 groups, or C and D are linear and quadratic slopes for a numeric variable that you want to have both. Yeah, there's different kinds of situations in which you are logically forced to add multiple slopes at the same time to fully cover something. And so then this is like the new concept for this unit is how do you test the new contribution of multiple things at the same time? It's still an F-test, but it would be an F-test with 2 degrees of freedom for just these 2 new things, to lump them together specifically, not all 4. So wrapping this into some kind of summary then, the F-test for the model is for all the slopes. To assess the change in the R square that results from adding new slopes, you don't have to do anything if you've only added one new one. If you've done more than one new one, that's where we have to ask for a separate F-test. And then the examples I want to show you today are designed to help you get that more easily, especially for Stata users. You're going to like this one. There's one line of code that does all of homework 4 in Stata. I'm not kidding. 1. Did you try this Stata? Not yet? Okay, nest egg. Nest egg for the win. So the rest of this, before we get into an example, is some sort of like weird stuff that can happen that I wanted you to be aware of. But before we do that, questions or any of this that you want to hear again on this slide? No, we're feeling okay with this? Okay enough, anyway? All right. So, weird stuff that can happen. There is a term that you will hear occasionally called suppression. It sounds like a problem to be solved. It's not. It's what happens essentially when your predictors are correlated in opposite directions. The corresponding regression slopes can change in ways that you would not expect. So in general, if you have a predictor that is correlated with other predictors in the model, its slope is going to be different if it's with those other predictors than if it's by itself. Because when it's by itself, it reflects the full relationship between that predictor and outcome. When it's with other predictors, it's the unique relationship after controlling for the other stuff. So those aren't going to be the same ideas. Generally speaking, the effect size for your predictor will be smaller when it's in a model with other predictors because it has less unique effect that it can have. The other predictors are fighting against it. In general, that is the case. But that is not always going to happen because of weird situations like these. It happens if the correlation of the outcome with 2 hypothetical predictors in this example are both positive, and then any of these things is true, and I've highlighted this one here because this is the one in which I've seen it the most, if the 2 predictors are negatively correlated, then you can see some weird stuff happen. So as an example, from the Cohen, Aiken, and West regression textbook. If Y is sales success in people who sell things for a living, X1 is assertiveness, so you would expect that being assertive leads to better salesmanship, and X2 is record-keeping diligence, also good for being a good salesperson. Are assertive people anal retentive in their record keeping? Not necessarily. So in this example data, there is a negative correlation that says, nope, the more assertive you are, the sloppier you are with respect to your records. The undiligent you are. Is that a word? Indiligent? Any grammarians in here? Undiligent. I'm going with it. I'm making up words today. So the outcome of sales success and assertiveness is correlated 0.4. Fine. The outcome of sales success and record keeping is less correlated, and the two of those are negative. So what ends up happening is that the effect sizes for these terms in the model are actually stronger than their bivariate effects would reveal. So the moral of the story is that common advice to look at a correlation matrix, see what's related to your outcome, and then only include the things that are related to your outcome in subsequent analyses, that can go awry because of this. What a predictor contributes by itself is not necessarily indicative of what it contributes in combination with other stuff. You got to know how it's related to the other stuff. So everything is up for grabs with respect to that. Make sense? Makes sense. All right, here's some tables that I stole from the person who taught me undergrad research methods in statistics, Cal Garvin at the University of Nebraska-Lincoln, just retired, I think, a year or two ago. Thank you for your service. So this is SPSS output. It's like a throwback. So this is a correlation matrix from SPSS output in which I have a Y and I have 5 X's. And the first row in each of these cells is the Pearson correlation. The second row is the corresponding p-value for its significance, and the last row is sample size. And I have this highlighted here, that in this correlation table, it looks like I got a pile of nothing. Each of these X's is uncorrelated with the outcome. Nevertheless, if I put them into a regression model, I do have significant slopes for some of them, and the model itself is significant. So you would not have anticipated that this could happen. But again, what a predictor contributes in conjunction with other stuff is not the same as what it predicts all by itself. And it's hard to anticipate how those things would differ. So this is most likely when the predictors themselves are not very related, and they can each make a stronger, unique contribution because they're not stepping on each other's toes. Here's another one. In this case, Y is across here, and I have 9 predictors. Each of these 9 predictors is unrelated to the outcome except for the first one. So I throw all 9 in my model, and unsurprisingly, the first one is still related, and the rest of these aren't. But my model is non-significant. The reason that the model is non-significant is because F is a per slope indication. So I have 1 good slope and 8 crappy ones. That's essentially bringing down my per slope average. So in this case, I would be inclined to simplify the model to take out all these unnecessary predictors. And in that event, the model might actually become significant because it's down to 1 slope, and it would be responsible for whatever variance that correlation implies. So 0.23 squared would be the R squared contributed just from this one thing. And here is a funny one. This one's probably my favorite. So I have a model that is decidedly significant. It accounts for 19% of the variance. There's my p-value. Yet I go down the list of all of my predictor slopes and their p-value in the last column, all non-significant. How can I have 5 non-significant slopes that work together to build a significant model? And feel free to read from the slide. Most of my answers are somewhere in front of us because I am shameless at encouraging audience participation. Yeah, these predictors are very highly related with each other. So that means what they can bring to the table uniquely is a lot smaller. But fortunately, in building an R-square, it's not just about each predictor's unique contribution. What else goes in? I'm making a little circle here, my diagrams. Remember the Venn diagrams? We got the X1 circle, the X2 circle, and the middle? The middle goes into R-square. The shared C area goes into R-square. It just looks like that none of these got individual credit. So this is like teamwork, right? There's no superstars on this team. Everybody's pulling their own weight, no one's standing out, and together, the team won. It's a beautiful analogy. We're talking about sports today. I was talking about sports in my other class somehow too. It works. So, in summary, here's everything I said over the last 2 weeks. I'm not going to read my slide to you, but I always try to have a summary slide to hit the high points. How are we doing, folks? Thumb check? How are we feeling, I should say? That's maybe a different question. Ish? Good-ish? Let me refine the question. How are we feeling about the material in this class? How are we feeling could be a lot of things, like, I like pizza. I'm looking forward to Friday. You know, like, those are my feelings. So mostly okay? Not as overwhelming? Okay, good. Let's do example 4B as a way to kind of like start back from the beginning, walk through some stuff, make sure that we're all on the same page. This is a new data set. So the general social survey data is gone. This is example 4B, materials for which are posted. These are fake data that I made up, but I made them up to look like a real data set that I have. These data are featured in chapter 2 of my longitudinal analysis textbook. The reason that these data are in this class is because I'm going to be using them to illustrate interaction terms as the next unit. And the reason that topic is in the longitudinal book is because nobody gets taught that. And I realized real quick in teaching longitudinal models that if you don't understand how to work with interaction terms, you are dead in the water. So I had to put that in as an early chapter. So even though we're not doing longitudinal analysis, this is an important precursor skill to that kind of thing. So here's the story. These are fake old people. Once upon a time, I used to work in the area of cognitive aging as a graduate student and postdoc, and so this is from that part of my life. These data were simulated to look like a real data set collected from the octogenarian twin study of aging in Sweden in the 1980s. So they studied same-sex twins starting from age 80 to 100 for 8 years in that study. So I simulated data from the baseline occasion using those variables and the story and the results. We're going to be predicting a measure of cognitive functioning. It's known as the information test. It's just a test of general knowledge. It's supposed to measure crystallized general intelligence, if you want to believe that. Since these are old people, we're going to control for their age in years. In the world of cognitive aging, you always have to control for age, or no one will listen to anything you say, because that's the uninteresting control variable. We're going to center age at 85 years, because that was the mean in that example. Next one we're going to have as a predictor is grip strength, measured in pounds per square inch. That face, like, what? That seems very random. It's not as random as you think. It's a little thing where you see how strong, how many pounds you can squeeze. It's supposed to be a proxy for physical health that's easily measured. Or frailty, I guess you might say. I know. I'm not a cognitive aging person in this moment. I'm a methodologist, but yeah, you're allowed to make that face all you want. Don't shoot the messenger. In that data set, the average was 9 pounds per square inch, and this varied by gender, as you might imagine. I have binary gender. Men are going to be the reference group. In this case, women is the alternative. And then last but not least, in the original study, they had variation in dementia diagnosis. So this was a longitudinal study. At the baseline occasion, there were actually some older adults who already had a dementia diagnosis as part of their profile. There were adults that over the 8 years eventually became, I want to say became demented. They satisfied the criteria for a dementia diagnosis. We're going to say it that way. And then, because this is Sweden and they can do things with data that we're not allowed to, they followed them all until the end. So we have death dates for everyone. We know what happened to them. And there are some people who were never diagnosed with dementia, ever. So this is an ordinal variable. I have the none group, the future group, and the current group with respect to this. So the folks who are never going to have dementia should have the best results. Those who are on their way there would have some kind of deficit probably, and those who already have it have a deficit because that's what dementia means, some kind of cognitive deficit in this case. We're going to treat this as a standard indicator-coded variable where none is the reference, so we'll contrast future versus none and current versus none. So then the steps of this analysis, we'll first look at descriptive statistics, we'll look at bivariate relationships with the predictors and the outcomes, or with the predictors, each set of predictors with the outcomes, and then we'll build up to a series of models. So that's my plan. Do we have a preference for Stata versus R code in terms of what goes first or what we talk about more? R. See, this is where like the YouTubers don't get to vote. Like if you're in this class and you're not here, you don't get a say, man. This is democracy, but you got to show up and vote, right? If you want to say in the democracy, tie into Tuesday. Hey, Coralville's getting a new rec center. Yay. I'm happy about this. The Coralville Rec Center is fabulous. My son really enjoys a lot of their programming. Any of you have elementary school kids? Anybody? No? They have a Nerf war sometimes on Saturday nights. Yeah, like they put up all these cardboard like structures in their gymnasium and they let the kids just go nuts with their Nerf guns, like screaming through the rec center. It's my son's favorite thing to do. So, here for that. They also hold video game tournaments periodically for kids. And he plays second in Mario Kart and in Smash Brothers. So, he's an overachiever. He's gifted and talented in that case. That is his sport. Yeah, continuing the sport is esports. That's what they call it, esports. It's a thing. Yeah, he's into esports. Hey, you know what? You're not going to get a concussion in esports, so I'm here for that.
Not like
You could. It's a lower risk, I would imagine. Like if someone gets mad at you for cheating in Mario Kart and throws the controller at your head, like that probably has happened, but maybe not the same level of damage as a 300-pound person knocking you to the ground, hypothetically. You can earn money? Oh, being knocked to the ground gets more money? Oh yeah, no, don't encourage him. He already thinks that he's going to open a YouTube channel and instantly be a millionaire. It's not how this works, but yeah, he wants to be an esports person too, and I don't know how lucrative that career choice is, but I can't imagine not very. Well, yeah, like if you're the best Smash Brothers person in the universe, then yeah, maybe you get all the endorsements, but the rest of the people, like that's not going to go well. So, anywho, long story short, you don't get to vote if you're not here. So democracy, R. Bringing it back. So you've seen most of this kind of code before, but I always want to show the complete record of how the data transformations happened. So note that I'm doing everything in like one giant block of code with respect to building my variables. This is what I would recommend. If you want your code to be easily used subsequently, I would not do the thing where it's like, make a variable, make a model, make a variable, make a model. Because then when you want to redo your data set, like bring it back with all the stuff in it, you have to like hunt and peck through your code to find all the parts that where you're building variables. Having them in one fell swoop makes that process easier. So I'm reading in my data set. In this case, it's an Excel format as usual. I'm going to make some new variables by centering. And so my new variable is age 85, because that tells me what the reference is here. Grip 9 pounds of grip strength is my reference for this as well. And this is another thing that I do that, admittedly, I am anal retentive in my record keeping. It is not a coincidence that this and this are the same length. I try to keep my names the same length so that my code stays aligned when I do things. It's just one of my little tricks that makes it easier to debug. It does. Then it looks more tabular and you can spot your errors more readily. So that's just a little pro tip. Dementia. So dem group is the original variable. So each of these statements is then saying, if group is this, then go do something else. So starting off by making two empty columns, I have dem NF, that stands for none versus future. Dem NC stands for none versus current. And then if dem group is 1, then take that first contrast and turn it into a 0. If group is 1, take the second contrast and turn it into a 0. So the fact that I've zeroed out both of my new contrast variables tells me what? That's my reference group. That's what my intercept is going to tell me, is that group's conditional mean. That's a choice. So then I'm turning the first contrast on if it's group 2. I'm turning the second contrast on if it's group 3. So these work like switches, essentially, to bring you off the reference group to each of the other groups. I have labels here and comments only because actual labels screw up the analysis sometimes, depending on which R package you're in. And then I have this. I don't know if you've seen an example of this yet. Is this new? I think it might be. Looks new? You can sort of tell what's happening based on the comments and the code. The question is why? So what this is doing is kicking out any rows that do not have data for all of these variables. Subsetting to complete cases. Now, why might I do this? That's my question.
Because if you're missing data for one of those, then it's going to mess with your model.
If I'm missing data for one of those, so let's, in this analysis, we'll start with examining age, then we'll add grip strength, then we'll add gender, then we'll add dementia group. So yeah, if I'm missing dementia group for somebody, that means that if I'm in a sequential model building, the people who are missing dem group would show up in all the initial models, but then they won't be in that one. So then it's like, oh, my sample size was 101. Oh, wait, now it's 99. Oh, wait, now it's 97. Oh, wait, now it's 96. And that gets confusing and can be inconsistent. So I'm dumping everybody who has incomplete information just down to those who are complete. And you're like, hey, Lisa, isn't it like bad to delete data? Isn't that somehow either cheating or suboptimal? Yes. Yes, yes, it is. But if you don't have a lot of missing data, this is a reasonable thing to do. If you have a lot of missing data, this is not a reasonable thing to do, and you need to take more coursework. The how to do it better is a longer, much longer explanation, but it is a whole field of research that there are techniques for addressing missing data. All of them require you to pretend that you know why it's missing, though. Because by definition, you lack the information to test it. So there are designations of missing data that you may come across. There's 3 levels of it. There is missing completely at random, which is exactly what it sounds like. Missing at random, which means it's random, but I know why. And then there's missing not at random, which is I have no idea why. And all of the techniques that are like in use are for the middle case. Missing at random meaning it's missing, but I know why. Meaning I've put other variables into the model that would be related to the missingness. So given that we don't have that whole set of ideas behind us, for now I will say this is my recommendation, but know that in practice, if you have a lot of missing data, this is not a good choice. It's called list-wise deletion, for those of you who may have heard that terminology, or case-wise deletion. But these are fake data. And you know what? When you make up fake people, they are really compliant. So I have all the data. It's fine. Much more so than actual people. All right. So we have some descriptive statistics in Stata and in R. So summarize is the command when you have numeric variables, as in Stata. In R, I've been using describe, but note here's something novel. Have you seen an R call that looks like this? Actually, let me zoom back out again. With the dot dots. So this is necessary whenever you have multiple packages in memory that use the same word for different functions. So I loaded a package called HMISC. I think it's, yeah, this is what it's called, that prints correlations and p-values in neat tables. And it warned me that that package has a function called describe as well, meaning that if you just write describe, it's ambiguous as to which one it's going to use. So this makes it so that it's pulling the function specifically from the psych package so that it's doing what I want it to. So I would say that if you want to be complete in your coding, that this is not a bad strategy to always adopt. Like, what package is this coming from? That way it's very clear to your reader where the stuff came from. Not common, but I think it's reasonable. So in terms of output, cognition on average is around 25 on a scale of 0 to 44. So this is a variable that's probably a little bit negatively skewed in that case. Age has a mean near 85 and a range from 80 to 97. Grip has a mean near 9 and ranges from 0 to 19. And then gender, the mean is 0.59, meaning 59% of the folks are the one group, which is women in this case. So why am I saying these things? This in particular, stop here. When you get a new data set or when you're analyzing data for the first time, make sure these numbers are in range. Garbage in, garbage out. If I have categories though, like dementia group, should I use describe or summarize for those? Dementia group was coded 1, 2, 3. Should I add that to this line? Probably not, right? It's not a number. So if I added dementia group to either of these calls, it would treat it as an actual numeric variable, so I don't want that. Instead, I'm going to do tabulate in Stata or prop table gives me proportions in R for my categorical variables. So for sure I need that for dementia group, and I also did that for completeness for binary gender. So 72% of my sample is in the none group with respect to dementia status, 20% is in the future, and only 7% is in the current. So most of the folks here are fine or are on their way to not fine. In terms of power, how do these proportions inform what I'm likely to see with respect to dementia group differences? Am I going to have equal power regardless of which two groups I'm talking about to compare them, do you think? What's going to happen? In particular, %7 of my sample is in group 3. Yeah, that one I'm not going to have as much power because I don't have as much people. So it's important to keep relative group size in mind when you're interpreting comparisons in unbalanced groups like this. It's not wrong to have them be unbalanced, but it just complicates comparisons. What about for binary gender? Is that one okay to treat as a numeric variable and estimate a mean and a standard deviation for it? I did it. Men versus women is not a number, right? We can agree on that. However, how many unit differences are there in men versus women? 1. So because of that, I can think of it as numeric. So the mean for this tells me the proportion of people who have a 1 value instead of a 0. And if I want to know the proportion of people who have a 0 instead, it's 1 minus this, so it still works. Okay, so univariates, that was our first unit. That was homework 1. So this is like a greatest hits collection, right? Literally, I'm taking you back through the semester so you can see how far you've come. This was homework 1. Open up Stata in R and fight with it for your very first time. Get descriptive statistics out and put them into a method section. Then, bivariate associations. Now, we did these predominantly through models, but a faster way to do it, if you're interested in linear relationships among numeric variables, or binary for that matter, is to estimate a correlation table. So in R, I'm using a function called rcore from the HMISC package because it provides a nice little table of p-values, whereas the standard core function does not. So here's a table of correlations. Here's the corresponding p-values. That same information is up here in the Stata output as the p-values underneath and the correlations on top. So I know the Stata folks aren't overly represented today, but I like the thing together at the same place. So we'll just look at this table for a second. Is age related to cognition? Correlation of negative 0.17, p-value of 0.0001. What happens as you get older? Yeah, these can be thumb questions too. Yep. Negative correlation is the disco move. As X goes up, Y goes down. Think John Travolta. He's getting old too. It's not a huge effect, but it is an effect. Is grip strength related to cognition? And it's positive. So if you want to get smarter, head to the gym. Problem solved. Is gender related to cognition? Which way? Men are the 0, women are the 1. Who's lower? You can say it, it's allowed. They're like, I'm going to get in trouble for this. I can feel it. Nope. Women are the 1. He's like, I'm playing it safe here. Men are lower, right? No, the women are the 1. The women are lower. However, even though these are fake people, I'm going to make up an actual theoretical reason. Differences in life expectancy. The dumb men already died. That's my simplest explanation. There is a selectivity effect. Women live longer than men, and people who die earlier die for reasons a lot of time. So if you put that together, it's kind of a non-comparable sample. But in this sample of fake people, I was just mimicking what happened in the original data. So it looks like all of these things on the surface are related to cognition, would be reasonable candidates for inclusion in a model. Now I am assuming a linear relationship between age and cognition and a linear relationship between grip and cognition. What if I wanted to put in a quadratic relationship instead? Or something, yeah, let's stick with that, quadratic. Can I throw that into my correlation table? I could put in age squared into my table. The problem is that the correlation between cognition and age squared does not tell me about the quadratic effect. It tells me about linear and quadratic at the same time. Because that partitioning of this is the linear term and this is the quadratic term only happens where they're in the same model. For the same reason, these two predictors are not in my correlation table. When they're together in the same model, they are interpreted as the first column tells me none versus future, the second column tells me none versus current. The way that happens is that at first I'm lumping together none and current, and then the second contrast shows up to pull those two apart. So they work together, it's teamwork. Now if I put each of these predictors by itself in the correlation table, this is no longer none versus current. What does it mean if you just look at the face of what the zeros and ones are coded as? Yeah, it's none and current versus future. And this one would be none and future versus current. So that doesn't make sense in a bivariate correlation table. So we're not going to go that way. What we're going to do is throw dementia group into a model so that we can look at how the group differences work together to create the three means that we need. I can put gender into this, though, because it's binary. However, you will learn in other coursework, hopefully, that for binary variables, other kinds of correlations work better. Particularly amongst two binary variables, Pearson correlations are a bad idea. Ordinal variables, it's the same thing. You would want something called a tetrachoric in that case, but that is not this class. Just planting seeds. Now, in terms of the correlations among my predictors, grip and age are negatively correlated. That's unsurprising. So the older you are, the weaker you are. Age and gender are not that highly correlated in this case, but sex and grip are. So they're correlated negative 0.4, the strongest relationship in the table. So that means that when we put gender into the model, it's going to fight it out with grip. So we would expect their effects to be smaller when they're together than when each is examining it, predicting it separately, because of that collinearity. All right, there's the same stuff. Here's the correlation matrix in R. There's the p-value table corresponding. All right, with me so far? Cool. So now we know that each predictor is related to the outcome. We know that there are relationships among the predictors. So let's build piece by piece. What I'm doing here is essentially trying to figure out a tournament of which terms I might carry with me to the full model and which ones I might leave out. So I know that age is related linearly to cognition. I want to examine the potential for a nonlinear relationship. So I'm going to do that by fitting a model where cognition is predicted from a linear effect of age and age squared. We're going to go straight to that. Does it look like age predicts cognition according to this model? I'll go down to the R code. Oh, no, I don't. R code's not there. You got to stick with data. At this stage, I went with either or. Does age predict cognition? What do I need to look at to answer that question? There's a lot of stuff here. Let me phrase it differently. To what extent does age significantly account for variance in cognition? Where do I look to answer that question? Yeah, my model. R squared of 0.03. Age is responsible for 3% of the variance in cognition. Is that significant? Yep. Here's my two slopes for age. So what's the pattern? According to this model, the fixed intercept is 24.6. Who is that for? 85-year-old. Here's my linear slope for age. It is significant, and it is negative 0.6. So for every year older you are, what happens? You go down by 0.6. And that's not the end of the sentence. Think sad face. Or happy face. Who is this the age slope for? 85-year-olds. That's the end of the sentence. So this is creating a U shape, which means the slope is different depending on where you are on the U. This is the slope at age 85 specifically. The quadratic slope does what to it as age increases? We have a positive linear slope, pause. Try again. We have a negative linear slope of age paired with a positive interaction term with age. Quadratic is age times age, foreshadowing for next week. What is happening to this linear slope as people get older? Is it speeding up or slowing down? We got one vote for speeding up. These are in opposite signs. Changing our answer? Slowing down? Speeding up would be a negative and a negative. Then it would be like a cliff that you're falling off. So this one, the quadratic is actually slowing it down. And the rule is multiply this sucker by 2. So the slope itself, that negative 0.6, becomes less negative by 2 times this number per year of age. The slope itself is slowing down per year of age by twice the quadratic. That's how I would interpret this. However, I already knew from my handy dandy correlation table that age is related to cognition by this much, right? Now I'm making age a more complicated version of the model, and it's still related to cognition. The question is, do I need this additional layer of complexity? Did adding the quadratic term help? Definitively no. You're correct. Why not?
Because I'm thinking that 90 is already 90.60, and then people cannot get the end of older limit.
Yeah, this p-value right here says that this quadratic slope is not different than 0. It would be expected, a slope this large or larger would be expected 58% of the time if it were actually 0. So well within expected territory. So this is an example of this concept. If I added one thing, so this is like going from linear age only in Model 2, which is the same thing as a Pearson correlation, and now I'm adding quadratic age. I don't have to do anything extra to assess whether that new predictor helped. The slope for the new predictor tells me so directly. So I know I did the math for this. Yep. So we have an r squared that's implied by this. Negative 0.17 squared would be the r squared. I have an r squared up to 0.03 here. So then the question is, how much did quadratic bring to the table? A non-significant amount, so we don't need it. So I'd say, no, I'm going to stick with linear age when I go and build my model. And our folks, the only thing to keep in mind when you do quadratics is this weirdness right here. Oh, there, I did do it. Yep. So linear age r squared is 0.029. We're up to like 0.0296 with quadratic. So it changed in the 4th decimal point. I'll call that 0. How about grip strength? Do you think it could have a nonlinear effect? Good. Empirical question, right? Now we have some R output for that. Does grip strength significantly predict cognition? Yeah, it's approaching. Well, this one is approaching significance. This one, yeah. This one is what I want, yeah. So in R output, the R squared is here, the p-value is here. So it looks like the model is significant. The two slopes work together. The question is, what does quadratic contribute? So if we go through the same process, now who is my intercept for? And don't say age 85, because age is not in the story right now.
People with 9 pounds of grip strength.
Yeah, 9 pounds per square inch specifically. What happens to predicted cognition in people that are stronger? Hit the gym. So this is the change in cognition per pound. Is that the end of the sentence? Nope. At 9. Same logic. It's at the 0 point of this predictor. And note that I am deliberately substituting in better word for unit. Like the generic, this is a change in y for a 1 unit change in x. Like, don't write your papers that way. People will hate you. It's per year, it's per pound, it's per inch, it's per whatever. Like, put the units in for your reader. And if you're dealing with a variable that doesn't have units, that seems like a bigger problem. Like per unit depression, it's like, what's that? For every additional score on this measure is what I would say, something like that. So if you're stronger, your cognition is better, higher, as evaluated at 9. What happens to the slope as you move up grip strength? Positive and a positive. Speeds up. This is that kind of acceleration pattern. However, not significantly. So it looks like the same story in the sense that there is a linear relationship. We learned that through the Pearson correlation. There's not an additional bendiness to the line that we would need to probably keep into our model. And again, comparing the R-squares. The linear only model, R-square is 0.0585, 0.0588. Again, change in the fourth decimal place. Dementia group. Now we're into homework 3 with the golf. And example 3. So you've seen a variant of this with low, medium, and upper for working class. Switch out the labels and it's the same logic. So I am fitting a model that is just the two dementia contrasts predicting cognition so that I can ascertain the same kind of bivariate information as I got in my correlation table. There in the correlation table, back up here, yep, like there's one answer for how related age and cognition are. It's this R, which we can talk about is R or R squared, whatever. I want to achieve the same endpoint with respect to dementia group, but I have to do it in a model. Because I want to know how related dementia is to cognition, the model R squared will tell me that. So it takes two slopes, so I can't throw it into a correlation matrix, but I can throw it into a model. And by the way, what would you call this setup if you have a categorical predictor of a numeric outcome? If people don't call it a general linear model, what do they call it? Starts with an A. It's an acronym. Well, the words start with A too. I'll give you a hint. There is a town off of Interstate 80 as you drive to Omaha that sounds really a lot like this word, and every time I pass that sign, I think of it. I don't know if that helps at all. You're thinking of the sign, right? Anvoca or something is like, there's a small town in Iowa that's like Anvoca. And every time I look at it, I'm like, oh, that's Ancova. Actually, very close. Drop the C. Anova. What would make it Ancova? What's the C stand for? C does stand for constant, but not today. Something. Close. Covariate, yes. So in that specific naming context, covariate means a numeric predictor. So if I had age in here too, as a main effect only, then this would be an ANCOVA. Because there's no other covariates, meaning numeric predictors, this is just one way analysis of variance, or ANOVA. That's what people would call this. So this tells me directly the predicted outcome for the reference group, and it tells me directly what the differences are for the other groups. And so I have 3 linear combinations that I would want to build out of this. What is the mean for each of the other groups? And then what is the mean difference that is implied by the model but not given directly? So you've seen this before. It's not different. So does dementia relate to cognition? Yes or no? Yeah. Yep, looks that way. By how much? A lot. Dementia is bad for you, okay? I would recommend not getting dementia. Yeah, I'm a public health specialist today. 18% of the variance in my fake people is attributable to dementia status. So if I take that R squared and unsquare it, now I have essentially the answer of how correlated dementia and cognition are in a correlation metric. I just had to work harder to get it. Does that make sense? The idea that you have to put these two contrasts in so you have a model R squared to talk about as a bivariate relation rather than a correlation. Correlation would be, how does dementia 1, 2, 3 correlate with cognition? That would make no sense because it's not a number. Given this coding scheme, who is the intercept for? And don't talk about age or grip strength because they're not in the story right now. Given my coding scheme, 27 is the expected cognition score for someone in what group? The none group. What happens if you're gonna get dementia? Goes down a lot. What if you already have it? It's already down. Are the two gonna get it, already got it groups different? Looks like they should be, right? So I'm comparing these two slopes to answer that question. It looks like the difference between these two is about 11. However, what was the caveat that I reminded you about a half hour ago based on group size?
But your current has less power.
Yeah, the current group is 7% of the sample. So even though 11 looks like it should be a big difference, we would still want to test it because it's possible that it's not significant because it's too sufficiently imprecise. Standard errors are going to be large given a small sample size. So this slope then tells us how future differs from none. The other slope tells us how current differs from none. And then here is the linear combination needed to get the means for each group, as well as the remaining contrast for the mean differences and corresponding effect sizes. So the only one that you absolutely would want to request is right here, -1 and 1. That's how you build the 11, 11 minus 5, or 16 minus 5. Survey says, yep, that difference of about 10 or 11 is significant. So it looks like all three groups differ significantly from each other with fairly large effect sizes. So that one, for instance, is a Cohen's d of -0.5, meaning a half a standard deviation difference. And then here's the corresponding R output in the usual way, and all fun with these. So this is how you build group-specific means. This is how you build all the mean differences. The only ones that you would need that are new information are these three. Those are the three new pieces of information that aren't already up in this table. However, in practice, I tend to write these all out anyway, just so they're all in one list, and you don't have to like keep scrolling across different sections of the output to figure everything out. So I added, here's the functions that I added a couple units ago. This is adding confidence intervals to the basic output, and this one is adding effect sizes for those linear contrasts as well. There. 305. How are we doing, folks? Not so bad? Now, what if we did everything all at once? Can we do that? I just did. So note the combined equation here. This is like the second round of the tournament because I'm not bringing in the quadratic effects of age or grip that I figured out I probably don't need. I am leaving in all the other terms that it looks like do contribute. So this model is answering a different question than any of the analyses that preceded it. All of the previous analyses are bivariate, meaning just these two variables at once. Is age related to cognition? Is grip related to cognition? Is dementia related to cognition? What's different about the question I'm answering when they're all together? How do I talk about that? Like, how do I explain that to a reader? Now I put them all in the same analysis to see. Zoomers, you can play too. Zoomers have been awfully quiet today. When would I want to do this? What separate question does it answer?
The unique impact.
Ding, ding,
or
ding.
relationship of each predictor.
Yep. So the words to insert in the sentence are still or unique. Does age still predict cognition after controlling for grip strength and dementia status? Does grip still predict cognition? Otherwise, you can say, does age uniquely predict cognition after factoring in all this other stuff? Either of those works. So this is asking essentially for the variables to be pitted against each other to see whether they each still matter. Maybe it's the case that women are weak, and once you control for the fact that this person is a man or a woman, grip strength doesn't matter anymore, right? Because those things were highly related. The older you are, the more likely you are to be diagnosed with dementia. By the time you are in your 80s, your rate is about 50%. It gets worse. So then maybe age doesn't matter after you control for dementia status. Those are the things that we would want to know. So here's the magic. Okay, nest egg, right here. One line of code, folks. Do you know what happens? All of this. I know. And this works with other commands in Stata, by the way, more generally. So what this is doing is building in a layer. So it's going to fit a model with just age, then it's going to add grip, then it's going to add this, then it's going to add this. And what's nice about it is that it's doing it all without you having to do anything. So here's the age model. Here's the age and grip model. Age, grip, and gender. Age, grip, gender, and dementia. And then this thing. So this is comparing across the models to see what the contribution is to the R-square at each step. So it tracks what is the R-square to begin with, what did it become, by how much did it increase, and it gives you a significance test as to whether that increase relative to the previous block is significant. So if you're doing homework with Stata, like literally this one line of code will answer about 98% of the questions on the homework. It's gorgeous. So you'll note that these two steps are technically unnecessary with respect to testing the change in R-square separately with an F. Do you know how I can tell that without even looking at the model results? There's a clue in this little table here.
Because you only added one slope.
Degrees of freedom 1. Yep, that means I added one thing. So if the p-value for that one new thing is significant, then this p-value for the one new thing is significant. So this is really the only step at which you would need to do a separate command, and this is what it's doing for you, to lump together the two new slopes for dementia group that result in an increase in the R-square of 0.178. Ta-da. In R, I skipped over this for a second, I had to do them myself. So I had to write like 4 lines of code instead. But it's not super onerous. Then we'll get to the combined model and all the effect sizes next time. All right, 311, we've hung in there. You should feel good about that. Yeah. How's the candy bag? Is there any left? Send it around again if so. I'm on a mission. Any questions before we call it a week? Not just a day? Yes?
You draft your square terms for your almost what your is there a possibility that you may have wanted to throw it in there just to make sure that the square term didn't get any additional?
Yeah, if I wanted to be absolutely certain that I'm not overlooking something, I might throw those in, expecting because the unique effects could be different than the bivariate effects. In this instance, I have the hindsight of having made up the data, so I know they're not there.
Right.
But in life,
especially
yes.
if, you know, you gather data, you have no idea you may want to.
Yeah, especially if the results were like sort of marginal, like it looked like it could be sort of iffy. But yeah, these were decidedly non-significant in the way I talk about them. So yeah, I felt like I had a license to leave them out. Yep, cool. All right then. So formative assessments and then homework the next week. Let me know if you need anything. Have good weekends. Thanks for being here.
I'm only online.
Oh yes, yeah, Hillary's office hours are not being held today and Michael's are on Zoom only tomorrow. Thank you for reminding me that. All right, bye for now, folks.